Welcome to Calorimetry, a branch of thermodynamics which measures heat. You've just witnessed the conversion of the chemical potential energy of methane into thermokinetic energy. Calorimetry is based on the first law of thermodynamics, which states that in a non-nuclear process, energy is neither created nor destroyed, only transferred. Now, the heat changes we'll be measuring in this experiment are called enthalpies, and they can have either a positive or negative value. If the enthalpy is negative, what that means is that heat is given off and the process is called exothermic. If the change absorbs heat, the enthalpy change is positive and the process is called endothermic. The metric unit of energy is called a joule. There is also another unit which is very commonly used, and that's called the calorie, which you all recognize. Now, it has now been defined that 4.184, exactly 4.184 joules is equal to exactly 1 calorie. When one talks about one's food and one's food intake as far as calories are concerned, the calorie that is referred to is a kilocalorie. That is, the dietary calorie, something contains so many calories, is actually 1,000 calories, so that the dietary calorie is actually 4.184 kilojoules. There are many different ways in which calorimetry affects our daily lives. To anybody concerned with weight gain or loss, the following information should be very important. Note that proteins and carbohydrates contain about 4 calories per gram, whereas fats contain about 9 calories per gram. Excess calories above those required for the metabolic requirements of our body are stored as fat. And for each 9 extra calories, you get 1 gram of fat. Calorimetry then allows you to calculate your weight change from consuming extra or fewer calories. Hurricanes are created under special conditions, but by and large are driven by the energy released when water vapor condenses to liquid water. Calorimetry will allow you to calculate this energy. You can also use calorimetry to determine how much ice you need to cool your iced tea. But I think at this point we should get back to the experiment we'll actually be doing. The most important concept in this experiment will be the specific heat. This is defined as the energy needed to raise 1 gram of the substance 1 K or 1 degree centigrade. Specific heat is always an endothermic procedure. That is, it takes energy to raise the temperature of any substance. In one experiment, we will actually measure the specific heat of a metal, but in all these experiments, we will determine the heat transfer using water as the heat sink or heat source. The amount of heat transferred then would be equal to the mass of the water times its temperature change times the specific heat of water, which at 15 degrees is 4.184 joules per gram per degree centigrade. You will carry out the following measurements. You will measure the specific heat of a metal. An interesting extension of specific heat for simple materials such as metals is the rule of Dulong and Petit. This relationship notes that the molar heat of many metals is approximately 25 joules per mole. This means that if you measure the specific heat of a metal, you can convert this into an atomic weight of the metal. Although not very accurate, atomic weights determined in this way were useful in placing elements in the proper position in the early development of the periodic table. Well, we'll now look more closely at measuring specific heat. First, you'll weigh the metal, and then you will heat it in a boiling water bath. To prepare the calorimeter, which will involve a couple of nested styrofoam cups, what you will do is you will weigh out a measured amount of water and then obtain the initial temperature of that water. Finally, you'll take the hot metal and add it to the calorimeter and its water, and then note the new temperature of the water. Well, let's get started and show you how this is done. We'll use an electronic analytical balance to measure the mass of the solid that we're using in this experiment. Now again, to use this balance, make sure all the doors are closed, make sure the balance is level, and read 0 to start out with, and then put the cylindrical tube on the notches and make a weigh. Put the solid in the tube, 0 to balance, again put the tube on the notches, and the difference between the two weights is the mass of your solid. In this experiment, what you're actually going to be measuring is the heat being given off by this metal when you put it in the water in the calorimetry. So we must first heat up this metal, and we'll use boiling water here. And to keep the moisture out of the tube here, we'll put a stopper on the top of the tube here so that the water vapor doesn't get in there. Now note, if you have this set up right, the level of the boiling water will be at or slightly above the level of the metal inside the tube. That way the tube is in contact with the boiling water at all points and you get more uniform heating. Now it's going to take about 10 minutes to get this to the point where it's uniformly about 100 degrees here. And so meanwhile we'll be doing the weighing of the calorimetry water. You will use a triple beam balance then to weigh out the water that you'll use in this experiment. Now the key word here is that you're weighing out the water. You will be putting it into a calorimetry cup, but the weight of the calorimetry cup is not very important. What is important is exactly how much water you do put in. Now to weigh this, what you should do, don't worry if the triple beam balance does not go exactly to 0. Make sure that all the weights are set to 0, but if the triple beam balance doesn't go exactly to 0, not to worry, because you could weigh the cups here and then make sure that when you weigh the cups, the triple beam balance does go back to 0. So with the empty cups on the balance, we have set the weights on the beams so that the beam reads exactly 0 here, so it is exactly level. So now we have a starting point for the empty cups, and now we will weigh the water. The weight of the cup is exactly 3.82 grams, and now we'll put the water in, and it is the mass of the water which we are most interested in. And so now we'll weigh it. The pointer is slightly over 4, so we have 54 point, and it is not quite to 0.1, so it's about 54.07 grams, which gives us a total weight of water of 50.25 grams. Well, we're all set to start the experiment. The temperature in this boiling water here is now 100.5. Why are we using a regular thermometer here? Why aren't we using the precision thermometer here? That's a good question. You should really know the answer. But anyhow, note how we've set this up. We put it in a 400 milliliter beaker because the precision thermometer here is very expensive. It is very top heavy. The styrofoam cups are very light, and this can fall over and break the thermometer. So we don't want that to happen. So we have set it in this setup here. Now, what we need to do at this point, we're all set to put the metal in here, except we must know the initial temperature of this water. The temperature of the metal then is 100.5 degrees, which is what the boiling water is reading at this point. Let's take a reading on the calorimeter, the precision thermometer here. Okay, here's our initial reading of the water in our calorimeter. I read this as 22.65. It just seems to be just a tad above the 22.6 mark. Well, let's get this experiment going here. We'll take this thermometer out. Be careful. Take the hot metal out and put it in, and here we go again. It's still going up a little bit. You can see it is at 28.20 about. Okay, that looks like it's pretty well settled down now. So, 28.35. Having collected the numbers, we can now calculate the mass and the temperature change of both the metal and the water, and we can also calculate the heat lost by the metal in terms of specific heat and the heat gained by the water. With the first law of thermodynamics and ignoring the calorimetry constant, we can calculate the specific heat of the metal. Using Dulong and Petit, we can then estimate the atomic weight of this metal. Well, let's go on. You will also measure the heat of solution of a solid. Here's an interesting real-life application of today's experiment. Rather than carrying around ice cubes or refrigerators, emergency squads and even some hospitals carry around these cold packs. Well, how do they work? Well, if all else fails, we should really look at the labels, so let's take a close-up on that. These cold packs contain solid ammonium nitrate and water. And to make them work, to get them to turn cold, what you do is you break the barrier between the solid ammonium nitrate and water, and the ammonium nitrate starts to dissolve in the water. As it dissolves, it turns out that this is a very endothermic process, and the temperature of the solution goes down. In doing today's experiments, perhaps you can come up with something equally as useful. You will also measure the heat of a reaction. To illustrate a reaction, we're going to take the reaction here of ammonia with HCl. This is an exothermic reaction. And so what I'm going to do, we have some ammonia in here right now. I'm going to take some HCl concentrated and just squirt it in. And you can also see the reaction, you can even hear the reaction, and if you can feel the reaction. You will also use a computer to collect data. Now, this is the setup. You have a temperature probe here inserted in the solution in the calorimeter. There is a magnetic stirring bar to stir the solution, and it's driven by a stirring motor. There is a digital analog converter, and of course, the computer. The calorimeter does not have a cover, and this is not good calorimetry technique, but in these reactions, it's more important to make sure that there is good stirring. So we want to make sure that the stir is working. Well, let's begin. Open the Logger Pro icon, select the calorimetry experiment. We're running a sodium hydroxide HCl acid-base reaction, and our sodium hydroxide solution is stirring, so we're ready to start. To start, click the Collect button. The initial temperature of the water starts recording immediately. At about 20 seconds, we'll add the HCl, and an immediate exotherm drives up the temperature of the reaction mixture. Note the oscillations of the monitor display. The electrons in the cathode ray tube are being affected by the magnetic field of the magnetic stirrer. The experiment is over in 2 minutes. We still need to get initial and final temperatures, and to do that, we click on Analyze, and then click and drag over the region we're interested in. Then click on Statistics. We use the mean for the initial temperature because it should be relatively constant. And we'll use the max for the final temperature because the reaction was exothermic. Well, with that, goodbye for now.